All right, welcome. Today, we're going to do something a little different. We're going to take just one exam question and completely deconstruct it to show you the amazing physics behind something we see every day, a car journey. We'll go from a complete standstill all the way to an emergency stop. So, here's the game plan. We'll kick things off with the forces that keep the car still. Then, we'll decode its journey using a motion graph. And finally, we'll get into the really crucial physics of how a car stops. Okay, let's dive right in. The whole scene we're about to explore starts from a really simple place. A car. Parked, not moving at all, just held in place by its handbrake. Now, have you ever actually stopped to think about what's physically happening when you pull up a handbrake? It seems so simple, but this lever is our way into the world of forces, pivots, and moments, which, believe it or not, is exactly where our exam question begins. So let's get right into our first big concept. We're going to see how that basic handbrake lever uses a core idea in physics, the principle of moments, to let a driver apply a massive amount of force with just a tiny little pull. So here it is, the first part of our question. And it's a real classic physics puzzle, you know? It's all about leverage. How can you get a bigger effect, a bigger turning moment, without actually having to push or pull any harder? To figure that out, we've got to be clear on what a moment even is. In physics, a moment is just the turning effect of a force, and the formula is super straightforward. It's just the force you apply, multiplied by the perpendicular distance from the pivot point. So, here's the key takeaway. If the force you're applying stays the same, the only way to make that moment bigger is to increase the distance from the pivot. For a handbrake, that just means pulling it from a point further away from where it pivots. A perfect answer might also say something like, increase the length of the lever arm. It's exactly the same idea. Okay, the handbrake is off, the car is on the move, and the story of its first 5 seconds is told right here in this graph. Now it's our job to be the detectives and decode what's going on. Let's take a good look at this thing. It's a velocity time graph. So, up the side, the vertical axis, you've got the car's speed. And along the bottom, the horizontal axis, you've got time. Every single point on this line tells us a piece of the story of the car's journey. All right, time to put on our detective hats again. We've been given a huge clue, the car's momentum at the 3-second mark. Our mission is to use that clue, plus the graph, to figure out the car's mass. Okay, let's break this down step by step. First things first, we rearrange our momentum equation to solve for what we want, which is mass. Step 2, we look at our graph. We find 3 seconds on the bottom, go up to the line, then look across, and you can see the velocity is exactly 15 meters per second. Finally, we just plug those numbers into our equation, and boom, there's our answer. The car's mass is 1,600 kilograms. See how we did that? We took the clue they gave us, the momentum, and combined it with the data we pulled right off the graph to find out something new. Okay, so we are not done with this graph yet. We figured out the car's mass, but the next big question is, how far did it actually go in those first 5 seconds? So, how in the world do you get distance from a graph that shows velocity and time? Well, this is a super cool trick, and a really useful one to remember. For any velocity time graph, the distance traveled is just the total area underneath the line. So, how do we find the area of this kind of weird shape? Easy. We just break it down into 2 simple bits we do know how to calculate. For the first 3 seconds, the car is accelerating, which gives us a nice, simple triangle. Then, from 3 to 5 seconds, it's at a constant speed, which makes a rectangle. All we have to do is find area of each shape and add them up. Add those 2 numbers together, and we've got it. The grand total distance traveled in those first 5 seconds is 52.5 meters. Nice. All right, let's get into the final part of our question. The car's moving, and that's great, but now we need to think about the physics of bringing it to a stop. And this is where things get really critical, especially when we talk about an emergency stop. Okay, notice how this question is different? We're shifting gears a bit. This isn't about plugging numbers into a formula. It's about connecting the physics to the real world. Why does being distracted behind the wheel make things so much more dangerous? To really nail this answer, we have to be clear on our terms. The total stopping distance isn't just one thing. It's actually 2 things added together. First, you have the thinking distance. That's how far the car goes while the driver is reacting. Then you add the braking distance, which is how far it travels once the brakes are actually on. So think of it like a chain reaction. First, a distraction happens. What does that do? It makes your reaction time longer. And while you're taking that extra split second to react, the car is still moving, right? That extra distance it travels is what increases the thinking distance. And since the thinking distance is 1/2 of the total stopping distance, the whole thing gets longer. It all links together. All right, last question. We've all heard brakes screech, and some of us have probably even smelled hot brakes. But why do they get hot? It all comes down to energy. Think about it. A moving car has a ton of energy. When you stop, that energy has to go somewhere. But where? Well, it all starts with friction. The moment you hit that brake pedal, you've got brake pads literally squeezing down hard on the wheel discs. That powerful friction force does what physicists call work to fight against the car's motion. And here's the magic of physics. The work done by that friction is basically an energy conversion machine. It takes all of the car's kinetic energy, that's the energy of motion, and transforms it into thermal energy. In other words, movement becomes heat. And that's exactly why your brakes get hot. So cool, right? So there you have it. From a simple handbrake lever all the way to an emergency stop, we've just unpacked the entire physics of a car journey, all hidden inside one single exam question. It really shows you that these principles are at work all around us. Which leads me to a final question for you. Where else do you see this stuff, moments, motion, energy transfers, in action in your day-to-day life?